So we have 40 plus participants as of 8:30, which is not a bad number. Wow, that's nice. Well, I guess people are just present here and having their breakfast in the meantime, very probably. That's fine. That's fine. That's all right. So let's get back to our slides. And before that, just a question. Do you have any questions about yesterday? Anything that has stuck in your mind? There was a question at the end of yesterday's session, right after we had finished. So now's the time to ask those questions. Okay, so let me know when you're wondering about something. Uh, as I mentioned yesterday, you are free to ask questions at any time during this course, but please do not try to exploit the breaks or try to ask questions after we are done, because we have other courses starting in the meantime. Okay, but you're always, of course, free to send emails about anything whenever you want to. Okay, in that case, since we have nothing to ask, let's switch to our slides. We had stopped right at virtual memory management. And things are very simple. Things are very, very simple, in fact, on the contrary of how they appear to be. I mean, they appear to be complicated, but in fact, they are very simple in the POSIX world. And the idea is that in order to accomplish, in order to achieve the isolation of the memory spaces allocated to processes, and uh, in order to enable basically processes to run, to execute, even though we do not have the minimum amount of memory required in order to run them. Those are the two main reasons that we have virtual memory management. So let's say that you have a process that requires 8 gigabytes of memory in order to store all of its variables. I mean, at the maximum. I mean, because as you know, since we have dynamic allocation, the exact memory requirement of a certain process, of course, varies in time. It is not fixed. Sometimes it allocates 10 gigabytes in order to accomplish something, and when it is done with it, it frees it. So the requirement, the memory requirement of a process changes in time. But let's say that the maximum required for a process throughout its lifetime is, I don't know, 10 gigabytes, but you only have 8. So thanks to virtual management, we can fit those processes into less than the maximum amount required. That's one of the main goals that we accomplish here. And how does it work? Well, as I said, a very simple principle. So here, for instance, in this figure on the right, so let's enlarge it a bit. So in this figure on the far right, we have physical memory. We have the actual random access memory. Oh, we have a request to join. Let's get that fellow in before we continue, even though he's too late. On the far right, we have the physical random access memory. So it has been divided into frames, into pages. Now, these are not bytes, 0, 1, 2, 3, all the way to 7. Those are not bytes. They are collections of bytes. They are batches, groups of bytes. In this particular case, we call them page frames. And the exact size of these page frames, well, it varies from hardware to hardware, from operating system to operating system. It is not something that is fixed. Okay. Well, in this case, what the operating system does, what the kernel does per process, is that it keeps for every process independently, it maintains a page table. So basically, this is just an array. It is just an array. It is an array of integers. And in this page table, it describes the location of each page in the process's virtual address space. So this is a table that contains indexes. And these indexes point to what? They point to actual locations on physical memory. Now, and what about the side of the process? Now, each entry in the page table either indicates the location of a virtual page in RAM or indicates that it currently resides on disk. Okay, so we can also hold in this page table an additional bit to also indicate whether that page is actually in memory or at the moment on the disk. So, number one, the process does not reside entirely on random access memory. Only a subset of it, not its entire memory requirements, only a subset of it resides, stays, lives on random access memory. Memory is organized in terms of pages. So the operating system manipulates the memory allocated to the process in terms of pages. It doesn't measure it in terms of bytes. It measures it in terms of pages. So it can allocate, for instance, 2 pages, 3 pages, 10, 15, 1000 pages of memory for a process. Now, from the process's point of view, it is under the impression that the entire memory is available. But at the moment, it is only occupying, for instance, in this particular case, 5 pages of memory from 0 all the way to 4. And it thinks, the process thinks it is under the illusion, aldanıyor. It is under the illusion that its addresses start from some low address, maybe, I don't know, maybe from 0, who knows, doesn't matter. And they go all the way up to a certain number. And it thinks that it is using the first 5 pages of random access memory. Whereas in reality, page 0, through the page table dedicated to this process, corresponds to the page frame number 4, as in this example of random access memory. Page number 1 corresponds to the, in fact, second one, or page 2 corresponds maybe to number 1077 in actual random access memory. Now, before we go further, what is that question? Mr. Yusuf says, can we request to operating system so it uses RAM directly instead of swap area? Now, who talked about swap? We didn't talk about swap yet. You cannot really, in this particular case, I would say no. I would say no, Mr. Yusuf. I mean, you don't really have a lot of say in the case of the memory management issues. I mean, it's, can you force it not to swap anything? Those are some really obscure system calls that you can use, but no, I mean, that is the same thing as saying, can I force the operating system to execute always my process and not allow others? No, you cannot do that. You cannot request it. I mean, you definitely cannot force it, but you cannot even request it to keep it there constantly. You can give it some priority to your process, so that it will, so the operating system will consider it a bit more important than the others. But when it comes to also memory, I mean, that is only a request. So you cannot really achieve it with certainty. But as I said previously, I mean, we will talk about the details of memory management on a specific week dedicated to it. For now, let's cover the basics. We have actual 5 pages in the process virtual address space. So we have addresses starting from maybe 0, 100 or whatever, going all the way to, who knows, so 1000, 5000 or whatever on the far left. So we have increasing virtual addresses. But in reality, the address of page 1 on the left in the virtual address space, which corresponds in the page table to number 2 page frame, maybe it is far away at the first or second or third gigabyte of memory in actual random access memory. So even though the process is under the illusion that it is using a contiguous and continuous addresses, virtual addresses, in reality, each page that it is using, each page on the left that is allocated to the process, in fact, can be located at a who knows arbitrary position in random access memory. Now, what's the advantage? The advantage is that as soon as you try to access, for instance, an address in the whatever address that is not present in your page table, so you try to access a certain address, I don't know, 7,500,000 or something byte directly, you try to access that pointer, and the operating system can very easily and very fast see that that address does not take place in your virtual address space, since it does not take place in your page table. If it cannot find that page in your page table, well, in that case, very easily it can determine that you have, in fact, carried out a segmentation fault. So it is very easy to determine, to establish whether you are accessing a permitted or non-permitted position in memory. But more importantly than that, this allows the operating system to protect processes from themselves. So if you try to, either with a bad intention or without a explicitly evil intention, to read or write another process's memory, this way the operating system can stop you. And more importantly, it can stop you from accessing the kernel's memory regions by strictly controlling how you reference the addresses through this page table that the operating system manipulates. And more importantly, of course, even more importantly than that, whenever you need additional memory, all it has to do is just increase this page table with additional pages. And whenever, for instance, there are page tables you are not using actively, it can very easily return them to RAM as free so that other processes can exploit them, and only bring them back whenever you try to access them, whenever you try to reference them. So in this way, basically, we have the operating system in the role of a juggler, if you will. Hani şu topları arkadaşlar, jonglörler var ya, havaya atanlar. The operating system is actually behaving like a juggler in this case, constantly, dynamically giving back and forth pages to processes as they need them. If it sees that a certain process is only using just 2 or 3 pages in its page table, the remaining ones are free to be returned, basically, to the other processes so that they can use them. So it's a very dynamic environment. And plus, if a certain process doesn't use any pages for a very long time, they can be, of course, stored on the disk. So that is the swap area, naturally. They can be stored on the disk, since we have spatial and temporal locality. Maybe you use certain variables at the beginning of your process, and you will not use them for the next 10 minutes. So why keep those long arrays, big data structures on RAM while some other processes are requesting memory? So what can the operating system do? It can take those pages from your process's virtual address space, put them on the hard drive, store them temporarily, allocate the newly freed random access memory area to other processes that need it right now. And by the time that you need those pages again, it can bring them back from the hard drive. So that's the entire swapping operation. But as I said, we will take a closer look to this in the upcoming weeks. Now, there was a question somewhere. And Mr. Mustafa says, where is the page table kept? It is kept in random access memory. So it is also in RAM. Remember when we said that the kernel keeps a lot of data structures right here in the top gray area? So here where all those tables take place. So this entire rectangle is an area dedicated to your process in memory. It contains, of course, the code, initialized data, uninitialized data, the heap, the stack, command line arguments, environmental variables, plus all the data structures that the kernel needs in order to handle, in order to manage this process. So the table for the page indexes, another table for the open files, another table for the signals to handle, etc., etc., etc. So also those tables are kept in the memory region allocated to the process. Any other questions? Okay. Now, as we said earlier, if a process tries to access an address for which there is no corresponding page table entry, it very simply receives the segmentation fault, which in terms of kernel terminology means that the process has received the SIGZEGV signal from the operating system. Now, receiving a signal, I mean, I don't know how you imagine it in your minds, but receiving a signal is basically as simple as somebody signaling you with a flashlight. Sanki birisi size el feneriyle uzaktan bir böyle ışığı açıp kapatması gibi bir şey arkadaşlar. Somebody is signaling you with a flashlight. There is no byte transaction. Nobody is sending you any data and you are not receiving any data. It's simply a signal. They just notify you that something happened. And there is a certain number of things that can happen. The number of signals is fixed. It can be a segmentation fault signal. It can be a termination signal, etc. So you can imagine it as multiple colors of flashlights. It can be a green light, a red light, a yellow light, and that's it. I mean, there is a certain fixed number of signals, işaretler, that you can receive. But there is no data transaction when you send or receive a signal. Basically, those signals, I mean, we will have a week dedicated to signals. Signals can be sent by the kernel to another process, or they can also be sent from one process to another for communication purposes. But most of the time, they are used in order to let the other process know that it is time to terminate. That is the most often frequent use of signals in the system programming context. In 99% of cases, signals are used in order to terminate a process. 99%. The other 1% is for very, very special communication situations. I mean, you can use signals for communication, but only if you have no other option, basically. It is a last resort, if you will. Now, as I said also earlier, a process's range of, we have a question. Mr. Muharrem says, is there a relationship between 6seg signal and segmentation fault? Well, Mr. Muharrem, as I just said, it's the same thing. A segmentation fault is the 6seg signal. So if you receive that signal in your process, that means it's a segmentation fault. So how does the kernel let you know that there has been a segmentation fault? It sends you that signal and the process immediately terminates. Because when the process receives the 6seg signal, that's it. It terminates immediately. Immediately. That's why your programs end so abruptly, suddenly, when there is a segmentation fault. I mean, that's what it means to have to experience a segmentation fault. Your process accesses a memory address that is not present in its page table. The operating system detects this. And what does it do? Sends a 6seg signal to your process, which in other words is known as a segmentation fault, and your process terminates very abruptly. And there is no way of stopping it, the termination, I mean. There is no way of postponing it. There is no bargaining, nothing. If you receive the 6seg signal, that's it, the process terminates. So it's an unforgivable mistake to access memory locations, or not to access, even to reference memory locations that do not belong to your process. It is as simple as that. So a process's range of valid virtual addresses, of course, can change over its lifetime as the kernel allocates and deallocates pages for the process. So the page table is a dynamic structure. It can increase and decrease depending on the memory requirements of a certain process. Now, if, for instance, in the extreme case where you need memory and everybody needs memory and there is no process that no process that can afford to have some of its memory moved to the hard disk so that they can make space for you, well, in that case, in that extreme situation, the operating system will simply tell you that there is no more memory left. It will give you the message, device out of memory, and that's it. And then the program will terminate. Or your malloc, of course, will return with an error. That's a very, of course, extreme case. It happens very rarely, especially if you have at least 4 or 8 gigabytes of RAM. Okay, virtual memory management, of course, separates the virtual address space of a process from the physical address space of RAM. Yes, that's what we said. And that brings us to the topic of the stack and the stack frames. Now, as you probably know from your past semesters, of course, we have a stack in every process. I mean, it is right here. I mean, the stack right here growing downwards. And why do we use the stack? We use the stack for 2 things in processes. One, in order to store local variables. All the local variables that are not static, all the local non-static variables live in the stack region of the memory of a process. And of course, the stack, as you remember from the data structures course, it has a last in first out structure. So such as organization, so that it grows downwards. So the last thing that is entered it is at the top of the stack. And the first thing to enter it is at the bottom of the stack. And the second purpose for which we use the stack is, of course, in order to store function parameters, function arguments, and naturally the return addresses of functions. So the more functions you call inside functions, a function that is called inside the function, inside the function. So basically, if you call a recursive function, that's a classic example, it uses very extensively the stack. So that is why if you do not have a stopping condition inside the recursive function, what is the error that we encounter? If you do not have a stopping condition, a stopping criteria in a recursive function, what is the error that we receive? What happens concerning the stack?
Stack overflow.
Yes, the stack overflows. In Java, it causes a stack overflow exception, and in C, it just tells you that the stack overflowed, and that's it. Your program terminates. Exactly. So let's get back. Okay, so that's why we use the stack. Now, on most other Unix implementations, the stack resides at the high end of memory and grows downwards. I mean, that's the standard POSIX way of doing things. Now, of course, we have the stack pointer, as you remember from your assembler courses, that tracks where exactly is the end of the stack, so that it will know where to place the next variable that you will need to include in the stack. Now, of course, this is the user stack, but there is also a kernel stack. Sometimes the term user stack is used to distinguish the stack we describe here from the kernel stack. And what is the kernel stack? The kernel stack, so this is the second stack, is also a per process memory region. However, it is maintained in kernel memory that is used as the stack for execution of the functions called internally during the execution of a system call. So let's say that you called a system, that you made a system call, but the system call also probably, maybe, makes function calls inside it. So it also requires a stack organization, some part of the memory to use in order to hold, in order to store the function parameters, in order to store the function's return addresses, in order to store the local variables. So what is it going to use? The system call. Is it going to use your process's stack, the actual stack that we saw just earlier? This one right here? Of course not. This is the stack that is dedicated only to the functions of your process, not the system calls. So for the system calls and the functions that are called inside the system calls, we have a separate stack, which is the kernel stack, which doesn't take place here. So it is located in kernel memory, and it is kept on a per process basis. So there is a separate kernel stack for every process. So it is not one global kernel stack. If you have 1,000 processes executing at the same time, that means you also have 1,000 kernel stacks, one kernel stack for each of those processes. Okay. Well, now we have finished the hard stuff, so let's get to the easy stuff. Now, I mean, I'm not going to tell you the details of command line arguments. I know that you have already used argc and argv in the past multiple times, naturally. I mean, this is the standard POSIX way of doing things. Now, every C program, of course, must have a function called main, as you know, since your first semester, which is where the execution of the program starts. And naturally, the main function has two parameters, argc and argv, with argc representing the number of command line arguments, and argv, of course, an array of pointers. It contains the command line arguments, starting with the name of the program. And of course, it has to terminate with a null, naturally. And that's it. I mean, that's already the stuff that you know. Here we have a simple example. So we have the main method, which simply prints on screen with printf the command line arguments that have been passed to this program. Just don't forget to always terminate with null your list of command line arguments. So nothing new here. You already know this stuff. Feel free to ask any questions if you need to. Now, something different is, of course, the list of environmental variables. Now, this is something that we use a bit rarely, to be honest. I mean, up until today, I only needed to use these like, I don't know, 3-4 times at maximum. You especially need to use them when you have some daemon programs, so not regular processes, but daemon processes. In those cases, they come in really handy. So basically, these environmental variables, which are shown right here, so right above the stack, this is where you have the environmental variables, also stored in the processes memory space. So you have separate copies per process, basically. So what are the environmental variables? So very simply, they are just variables that are provided to every process as it starts from the operating system. And they represent system-wide parameters. Many students have created analogies in the past with, you know, the stuff that you bring you when you go to a restaurant before you order something. Arkadaşlar küver var ya lokantalarda. Hani böyle siparişi vermeden önce şeyler geliyor. İşte ne bileyim böyle zeytinyağıdır, zeytindir falan. Exactly same thing. We have not ordered anything. We have not told them what kind of variables we have. This is the stuff that the operating system gives you without even asking. It tells you, hey man, here, this is the path variable of the system. So if you need to look for binary files, executable commands, ls, cd, cp, whatever, this is where you're going to find them. This is a path for them. If you want to look for library files, this is the path for the library files. If you want to know what is the current working directory, this is where it is, and so on and so on. So the environmental variables are variables that are provided by the operating system, and they also take place in the memory space, in the virtual memory space of every process. And they are inherited when a process is created. They are inherited from the parent process environment. And of course, since the child gets a copy of its parent's environment at the time that it is created, this transfer is of course in one way and once only. After the child process has been created, the child process can change those variables as it sees fit, without without the danger of modifying the copies that are in its parent's memory space. So every process has its own set of environmental variable copies. Keep that in mind. So they are not global variables that are shared by all the processes. Every process has its own set of environmental variables. Here we have, for instance, an example. If you want to use them, you need to include, of course, the standard library, stdlib, and the Unix standard library header files. And we have, of course, the environ list of pointers. And here, simply, very simply, we just print on screen whatever the operating system has passed to this process as list of environmental variables. You are welcome to try, of course, these programs at home. Any questions about environmental variables?
Sir, may I ask you a question?
Yes, Mr. Bilal.
Sir, you said that environmental variables are passed by inheritance, but what if the computer shut down? How it started from the first process, the init, where the environmental list comes from?
Well, the init process, remember, the init process is not created by another process. The init process is the first process, and it is specifically created by the kernel itself. So it is the first process, so that is why it doesn't have a parent. It is its own parent. It's a very special process in this case. And since it is created by the kernel itself, and the environmental variables are given to it, of course, by the kernel itself. That's the only exception to the rule. That is the very special first process created directly by the kernel. So not by forking and execing. All the other processes, though, except for init, all the other processes, though, except for init, are created in the same way. Fork and exec with a copy of whatever variables the parent had. And after you receive that copy, the child process is free to modify it in whatever way it sees fit. But of course, if the computer shuts down, well, that means the random access memory is reset. When the computer starts again, first it will create the init process. the kernel will give it the default environmental variables, the default ones for the user that is just logged in, because every user account can have different environmental variables. For instance, the home folder, the path for the home folder is different for every user. So as soon as a user logs in, his process, of course, will have a separate set of environmental variables, and every other process that will be created afterwards will receive those copies. Any other questions? Okay. It would be nice to have a homework that also uses environmental variables. It has been quite a lot of semesters that we didn't have a homework with environmental variables. I will keep that in mind. Your first homework will come in next week, by the way. So here we have additionally some C library functions that you can use in order to manipulate environmental variables. So you can use getenv in order to access, retrieve the values of certain environmental variables. So you give the name of the variable and it returns you the value of that variable. You can use putenv in order to create an you can use putenv and putenv in order to create environmental variables, setenv in order to modify their values, unsetenv in order to remove them, and clearenv in order to clear the entire set of environmental variables. Okay, here in the previous example, for instance, we used what? We used puts in order to go across the entire list. So here in this example, for instance, the environ array contains all the environmental variables as a null terminated list of pointers. And we simply just printed them on screen one by one. Nothing fancy. It's just a list of strings. That's all. A null terminated list of strings. Now, this brings us to the topic of memory allocation. Now, of course, this is not the first time that you encounter the term memory allocation. This is not the first time that you have allocated, that you are going to allocate memory on the heap. You have already used the malloc function in the past, naturally, during especially the data structures course, I believe, I think. Or am I mistaken? I mean, you have used the malloc functions before, right?
Of course,
yes, we do.
Of course, excellent. So do you know the difference between malloc and calloc?
Calloc initialize the data, malloc does not.
Yes, excellent. So you have also used realloc?
Yes.
Excellent. So in that case, we are free to push the homeworks to the limits as far as the use of those system calls of those library functions are concerned. Now, it might come as a surprise, but malloc, in fact, and realloc and calloc are not system calls. They are just library functions, C library functions. That's something interesting. Now, allocating memory on the heap, of course, why do we do it? Because, well, in several cases, we have no a priori information about how much memory we are going to need in our process. So that is why we need some way of allocating dynamically. By dynamically, I mean while the process is executing, we determine how much memory we are going to need. And of course, we need to be able to ask the operating system to provide us that amount of memory. Now, remember the program break, PB, the program break right here. Right here, the program break. It represents the end of the heap. Now, there are some questions now to answer concerning the use of the heap. Now, what we know is that if you allocate memory, so let's say by calling malloc, the program break, if there is no available memory, free memory inside the heap, so let's say that you already allocated 1 GB, but you need some more. You are already using the 1 GB, so you need 100 megabytes more. Well, that means the heap has to grow. And what does it mean for the heap to grow? Basically, it means that the program break must move upwards. So the program break is something similar to the stack pointer that we use with the stack. Okay, so it is called the program break, the proper system programming terminology. So the current limit of the heap is referred to as the program break. And in order to allocate memory, of course, we have three functions: malloc, calloc, realloc, plus of course free, the fourth function, in order to free it. Okay, so what do we do with it? Now, besides malloc and calloc, what you don't usually use is of course break and sbreak. Now this is very rarely used, to be honest. Now break and sbreak are used in order to resize the heap. Resize the heap. And these are the ones that are actually system calls. Break and sbreak are actually system calls. Malloc, realloc, and calloc are not system calls. They are just library functions that rely on break and sbreak. Mr. Yusuf says, in the OS course, I've heard the global variables are also stored in the heap. Is that the same heap we're talking about? Mr. Yusuf, there is only one heap. There is only one heap. And it is right here. There is only one heap. And global variables are not stored in the heap. Global variables are not stored in the heap. What you can do is, if you define a global variable, regardless of whether it is static or not, initialized or not initialized, it will be stored in the data segment. So right here, if it is initialized, it will be here. If it is uninitialized at the start of the program, it will be here in BSS. This is where the global variables live. This is where they live. So the heap is dedicated. So the heap is dedicated to dynamically allocated memory. Now, but look at it this way. Let's say that you declared globally a pointer. You declared globally a pointer. So how many bytes do you need in order to store a pointer in C? How many bytes do you need in order to store a pointer in C? An integer pointer. Might be 4. Well, in Java, it is always 4. In Java, it is always 4 bytes. In C, it depends on the type of the pointer. Whether it is it depends on what kind of a addressing system you're using. It depends on whether it is a 32-bit system, a 64-bit system. It depends on the length of the addresses. In Java, it is always 4 bytes. So what does it mean to store a global variable in the heap? Because we have already said very clearly that global variables they are stored in the data segment. So the idea is the following. If you declare a global variable, I don't know, an integer, for instance, it will definitely live in the data segment. So if it is initialized right here, and if it is uninitialized in the BSS segment. But let's say that you declared a pointer. Now, that pointer, 4 bytes or 8 bytes, depending on the addressing system, will also naturally live in the data segment. So either in the uninitialized data or initialized data. Now, so since it is uninitialized, because it is simply a pointer, so it is, I don't know, if you have not set it equal to anything, it will be in uninitialized data. If you have set it equal to null, it will be in the initialized data. But you are not, of course, intending to use it simply as an empty pointer. Maybe during the course of the execution of your program, you are going to call malloc, allocate some memory, and give that address of the allocated memory to that pointer. So in that case, the region of memory that you have allocated lives in the heap. So let's say that you allocated 100 megabytes. Those 100 megabytes will come from the heap, but the pointer that holds the address of those 100 megabytes will be in the data segment. So that's what it means to have actually a global variable in the heap. The pointer is always, of course, in the data segment, since it is a global variable. But since we have allocated from the heap, the data is coming from the heap. But be careful. Global variables, by default, live in the data segment. I hope I have made this clear. Anlaşıldı mı Yusuf Bey? Okay. So let's get back to memory. Okay, so break and sbreak, the system calls that are behind malloc and realloc and calloc, etc., etc. Now, initially, the program break lies just past the end of the uninitialized data segment, as we saw in our figure just before. Now, if the program break is increased, so if you push that limit upwards, then the program may access any address in the newly allocated area. It can access it if it wants to, but no physical memory pages are allocated yet. The kernel will automatically allocate new physical pages on the first attempt by the process to access addresses in those pages. So be careful, it's a two-stage process. So if you want more region of memory, what you do is you push the program break upwards. So the heap is getting bigger in this case. But just because you push the program break a bit higher, and so now you have access to 100 more megabytes, it doesn't mean necessarily that the kernel has already set aside page tables for you. No, it will set aside those page tables at the moment, at the first attempt that you will make to actually access those addresses. Now, this is the same thing as saying, I just bought 2 more houses, but the houses will only become yours if you start living in them. So the moment that you go and try to open the door of the house that you have bought, only then does it become truly yours. Before that, it's just 2 houses that you own, but you do not yet really own them. They are not really yours. They only become yours when you try to open the door. Now, break and sbreak, how do they work? Break returns 0 on success, -1 on error, a regular system call that adheres by the tradition. And sbreak, it returns the previous program break on success or -1 on error. So you're simply asking it, where is the program break? Okay, they also receive some parameters. Now, the parameter for break, of course, is the amount by which we want to push the program break. So we are telling it, for instance, to push it for how many more bytes. Now, in your regular programming lives, you will not be using break and sbreak. I mean, there is almost nobody that uses break and sbreak in order to manipulate memory. It is too much prone to error. And instead, in 99% of cases, you will be using malloc, realloc, calloc, and free. But just for the sake of comprehension, here we have this slide in order to explain to you that behind malloc and realloc and calloc, we have break and sbreak. So when malloc actually allocates memory, it might use the break system call. Now, why might? Why am I saying might? Because the malloc system call, the malloc library function is used in order to allocate memory. We all know that. But let's say that you try to allocate 1 megabyte of memory. Why not? 1024 kilobytes. The first thing that malloc will do is it will check whether there is a free block of 1 megabyte in the heap. If it is free, it will allocate it to you. It will note it down in the page, it will note it down in the data structures kept by the kernel as allocated and no longer free. And it will return the address of the first byte of those 1024 kilobytes. If, however, there is no 1 megabyte free region in the heap, then and only then it will call break in order to increase the total heap area. That's why I said it might use break. So it's a two-stage process when you call malloc or realloc or calloc. It first checks whether the amount of memory that you requested is available in the heap. If it is available, it notes it down as no longer available, and it gives you the address of the first byte. But if it is not available, if there is no empty block equal to the amount of memory that you requested, then and only then it will call break, the system call that we saw, in order to increase the heap. So why do we use malloc instead of break and sbreak? because, well, they are standardized as part of the C languages, easier to use in threaded programs, especially in multi-threaded programs. They provide a simple interface that allows memory to be allocated in small units instead of having to deal with break and S break and etc. etc. And of course, they also allow us to arbitrarily deallocate blocks of memory. So this is something that is not easy to do with break and S break, which are maintained on a free list and recycled in future calls to allocate memory. Any questions about malloc and free at this stage?
Sure, not
Yes.
about malloc and free, but I couldn't comprehend the difference between break and S break.
The difference between break and S break. Okay. Let's do it this way then. Let's look at directly the man pages. I mean, this is what you do whenever you have any questions about system calls. So let's look at the documentation. So here we have break and S break. So we can use them in two different ways. We can directly give an address. You can see the screen, right?
Yes, we can.
Excellent. So, description. What does break and S break do? Break and S break change the location of the program break. And what is the program break? It is basically the sign, if you will, just like the stack pointer, the variable, if you will, that denotes, that represents the end of the process's data segment. Or in other words, the program break is the first location after the end of the uninitialized data segment. Increasing the program break has the effect of allocating memory to the process. Decreasing it, the break deallocates memory. So basically, using the break system call allows you to push this limit upwards or downwards. That is what break does. You give it a certain number. You give it a number of, I don't know, 10,000, and you push it upwards. You give it 5,000, and you push it downwards. So it allows you to move this limit up and down. But what about S break? S break increments the program's data space by increment bytes. Calling S break with an increment of 0 can be used to find the current location of the program break. And this is the actual use of S break. So let's say that you want to increase it or decrease it. What do? You call break. But how much memory do you have at the moment? I mean, where is the program break? Where is the program break? In order to know where it is, what is the current limit, that's why you use S break. You give it a parameter of 0, and then it will return the current location of the program break. So if you look at the return value, on success, S break returns the previous program break. Whereas break, well, it returns 0 on success because it is used in order to modify the program break. Is it clear now?
Yep, very clear.
Excellent. Keep it always in mind. Whenever you have any questions about system calls, the manual pages are your friend. They contain the entire documentation necessary for it, and it is accessible right from your keyboard. You don't even have to be online for it. Just open a terminal and type man space name of the system call, and that's it. So nothing new about malloc. I mean, you know it. You have known it for quite a while. You just give it the number of bytes that you need, and if it is successful, it will return you the pointer to the first byte in the block of memory that you requested. And of course, it will return null if it is unsuccessful. And naturally, the difference between malloc and calloc is that with malloc, the amount of memory that is returned is not initialized. So it contains who knows what. It might contain data from previous processes. It can contain anything. So keep in mind that you should always, always, always check what malloc returns. If it returns null, well, you need to take the appropriate precautions. So never make the assumption that malloc will be successful. What about free? Well, free basically it is a very fast function, which very simply tells the kernel that we no longer need a certain block of memory. Now be careful. Free does not necessarily lower the program break. It just tells the kernel that you know that 1 megabyte of memory that we were using, well, we no longer need it. We no longer need it. So if there is somebody else, if there is another variable in the same process that needs it, you can allocate it to it. If somebody calls malloc or calloc, you can use it. So free simply tells the kernel that this certain piece of memory in the heap is no longer used. It doesn't lower the program break. Be careful for that. I mean, not necessarily, at least. A question from students, because we always know, I mean, we know. What do we know? We know that when the process terminates, all the memory allocated by it will be returned to the system automatically. All of it. All of it will be returned to the system when the process terminates. So students often ask, why do we have to free? I mean, if the system is going to take it back anyhow, I mean, why are we so anxious? Why are we so adamant? Why do we always insist on freeing memory? Now, when a process terminates, all of its memory is returned to the system, including heap memory allocated by functions in the malloc package. In programs that allocate memory and continue using it until program termination, it is common to omit calls to free, relying on this behavior to automatically free their memory. Although relying on process termination to automatically free memory is acceptable for many programs, there are many reasons why it can be desirable to explicitly free all allocated memory. Now, freeing it, of course, the main advantage that you have for freeing it is basically when do you free it? You do not wait until the end of the program in order to free it. You free it the moment that it no longer is necessary for you. The moment that a certain block of memory in the heap is no longer necessary, you must free it. Why? So that if there is another call to malloc or calloc or realloc in order to allocate memory, it will be able to use that region without having to increase the program break. So long story short, for memory efficiency. Now, especially if this is a long running program, especially if your process is going to run for a long time, you especially need to adhere, you need to conform by this rule if you do not want to cause memory leaks, if you do not want to have a program that constantly increases its memory consumption without ever ending it. So the main reason is for memory efficiency, especially if your process is executing in a memory resource limited environment, in a Raspberry Pi, in an embedded system, and so on. And especially even if it is a desktop or a server, if that program intends to run for a long time. If it intends to run for a long time, it needs to be very careful how it manipulates memory and free it the moment that it no longer needs it. That's the main idea. And that is what is expected in your homeworks. Free it the moment that you no longer need it. And once you reach the end of your program, free it explicitly without waiting for the operating system to clean up after you. This is what is expected in your homeworks. It will be also written in detail in the homework specifications. If you do not do this, you will lose marks. The difference between malloc and calloc, naturally, they do the same thing, just they have a different set of parameters. Malloc admits directly the number of bytes that you want to allocate. Calloc admits the size of a certain data unit plus the number of times that you want it. And the main difference is that calloc initializes the memory to 0 before providing it to your use. They return the same things, the pointer to the first memory address that has been allocated or null on error. So always check for the return value of calloc when using it. And of course, we also have realloc, and we need to be careful with it. So realloc is used for what? It is a function that is used to resize a block of memory. So you used malloc, you allocated some memory, I don't know, 1 megabyte, why not? And you have now noticed that 1 megabyte is not enough for that data structure, array, hash table, linked list, or whatever. And now you need 2 megabytes. Well, so what do? One option is you call malloc and you allocate 2 megabytes, and then you copy everything from the initial 1 megabyte block of memory into the new block of memory, or you can simply call realloc. You can simply call realloc. The PTR argument is a pointer to the block of memory that is to be resized. The size argument specifies the desired new size of the block. On success, realloc will return a pointer to the location of the resized block. This may be different, of course, from its location before the call. And of course, an error, it will return null. So be very careful when using realloc. Why? Because maybe, just maybe, you had a data structure that was taking 1 megabyte, living in the heap that you allocated, on a region that you allocated with malloc. Then you notice that that region of memory is not sufficient for you. So you need a larger area. So you call realloc. Now realloc has given you 2 megabytes. Okay, that's fine. Maybe it is the same region of memory that was extended by 1 megabyte more, but maybe it is a completely new region of the memory that is 2 megabyte large. So the addresses are no longer the same. Previously, the linked list that you had in that 1 megabyte had different addresses, and now it has completely other addresses. So be careful. The new larger amount of the new larger block of memory that you allocate with realloc can be located at a different location with respect to the initial smaller block of memory. Always keep that in mind. And finally, alloca. Now this is a function just like the malloc, calloc, realloc family, but I mean I'm almost 40 years old and I have never used this function. I mean, I have never used it, but it is good to know that it exists. It is a very obscure and very rarely used function, but it can be useful. Now, alloca is like malloc. You can use it. It has the same parameters like malloc. It can be used in order to allocate memory, but the main difference between malloc and alloca is that alloca allocates memory not from the heap, but from the stack. It allocates memory from the stack by simply increasing the size of the stack frame, by pushing basically the stack pointer upwards. Size specifies the number of bytes to allocate, and alloca returns the pointer to the allocated memory as its function results. Difference: never call free on a region of memory that you have allocated with alloca. Why use alloca? Because it is extremely fast. Extremely fast. Why is it fast? Let's look at why malloc is slow. Malloc is slow because it needs to check whether there is a part in the heap that is available for 1 megabyte. So it needs to go through the portions of memory that are free or not. It needs to make some calculations. Alloca doesn't have any calculations. You call alloca, it just pushes the stack pointer upwards. That's it. Extremely fast. And you do not have to worry about freeing it. You don't have to worry about freeing it, because the moment that it goes out of scope, that's it. It also disappears. It is not possible, of course, to use realloc or free with alloca, and of course you cannot use it within a function argument list. So in case you need very fastly very rapidly to obtain some dynamic memory, alloca is an option. Of course, the advantages, as I said, it is faster than malloc, since alloca is implemented by the compiler as an inline code that simply adjusts the stack pointer. Alloca doesn't need to maintain a list of free blocks, and it is automatically freed when the allocating function returns. So very fast for dynamic allocation, but also very dangerous since it can cause stack overflows, and unsupported by standard ANSI C, and so it means that it has limited portability. So use it very carefully, or very simply just use malloc instead. And that's it for today's class. Any questions? What I recommend to you is to read the chapters concerning next week's topics, because it will be a bit complicated, and next week you will be receiving your first homework. Thank you very much for your attendance. Any questions are welcome. You can send emails whenever you want to about anything, and I will do my best to answer them. Make sure that you have already installed Ubuntu or whatever flavor of Linux you want, not macOS, not Solaris or anything. We will be working with Linux. You can use any flavor of Linux that you want, any version, that's okay. Yeah, that's it basically.
Have a nice day, sir.
Thank you. Thank you, class. You too. Take care, and I will see you next week.
Thank you, sir. Have a nice day.
Thank you. You too.